Hi. If you're watching this video, hopefully you're looking to get a little bit of Regents review while the New York State Chemistry Regents still exists the way that it does. Just a quick introduction, some best practices before we get started. The number one most important thing you can have available is right here. It's a QR code that's going to point you to the New York State chemistry reference tables. It has all of the information that you will get when you take the test, and arguably a lot of the information you're going to need to take the test. Things otherwise you might want to have, some sort of a calculator handy. And if you need a paper copy or digital copy of the Regents, there will be a link below. It is suggested that you take a look at these questions before you watch this video. It might move a little bit fast for some people, but hopefully you find this helpful, and let's get started. Part B-2. So big changes here. First, it's fewer questions. We're only looking at 15 total, but second, the questions are grouped. You're given a set of data and you have to look at it. Third, you're recording your answers in an answer booklet. And you can see here I've taken a screenshot of the answer booklet. Some of the questions have you looking at like specific prompts for what you need to write, and then others you have this big open space that you're just going to fill. But your answers need to be there, because if they're not there, they don't get graded. Again, we are implementing a lot of these using models, computational thinking, analyzing and interpreting data. This is fewer definitions, not chronological. And then, like I said, you might see one prompt that has information about a bunch of questions, like this one right here. The questions are never related to each other. So we're going to dive right in. We're going to go 51 to 53. I'm going to write on the side. We're taking these in chunks. We have 4 naturally occurring isotopes of sulfur, S32 up through S36. Here are our abundances. We want the number of protons and the number of neutrons in the S33 atoms. So I've copied over S's atomic information from the periodic table. You can see a 16 for the atomic number. So first, the lower number, atomic number, number of protons. Oh, I did that backwards in the last video. Oh, my bad. That should be Z. It's AZX notation. The number 33 here, when you write it like this is what we call a mass number. And mass numbers, we saw this earlier in the review, mass numbers is the sum of the protons and the neutrons. The electrons don't really count because they don't really have mass in a appreciable quantity compared to the proton and the neutron. So here, if we know that the protons is 16 and the total is 33, all we have to do is add, and we get 17 neutrons. So we're going to have to report both of those in our answer booklet. I'm not going to adhere super close to what the answer booklet needs to show just for space reasons, but we should be recording 16 protons and 17 neutrons for 51. For 52, we need to calculate the atomic mass of sulfur. The atomic mass is the weighted average of the isotopes. So we need the atomic masses and the abundances. They're written here as a percentage. We need to turn that into a decimal. There are 2 ways to do that. One would be to divide your whole equation by 100. The other is to just shift our decimal point 2 places to the left. And we need to do that for all of these. To show all of our setup, now it does say show a numerical setup, so you don't have to calculate it. I'm willing to bet that if you calculated it, you'd get the atomic mass of 32.065. That's a good way to check that you're right, because if this is all the information, the test is internally consistent like that. So really quick, we're going to write things down, and it's going to be the mass of each isotope times its abundance. So the first one all the way through the last one. And I think the biggest area where there's going to be a pitfall is that after you shift all those decimal places, you have to make sure you record your decimals correctly. Another way to get around that would be to say 31.972U times 94.99 over 100. If you think that's a safer bet for you to not misplace your decimal point, that's a valid approach as well. And then for 53, compare the energy of electron in the third shell, the energy of electron in the first shell. So if we remember our Bohr model, we've got your nucleus, and then you have several shells of electrons. This is your first, your second, your third. As the electron is farther away, it is overcoming the attraction for the nucleus, so the electron needs more energy. It has more energy when it's in a higher energy state. If it doesn't have energy, it falls closer due to that electrostatic attraction. So you can simply answer this in a sentence. In the third shell, an electron has more energy than an electron in the first shell. The Regents is a little flexible to how complete your sentences are, but I usually find a complete sentence really communicates your understanding a lot better. Next 4 questions all have to do with this laboratory setup. We've got a ring stand, we've got filter paper, a funnel, and a beaker. So we're filtering a sample. We've got rock salt, which has sodium chloride solid, it says here, and some insoluble rock particles, literally rock salt. We're going to stir the sample of rock salt into water and then filter the mixture that you get afterwards. So other than mass, how do we know that the different properties, the different components have different properties? I think this word insoluble here is our biggest piece of information. I could go to table F to check the solubility of sodium chloride, but also hopefully at this point in the year, that's a piece of information that you've collected and you've taken ownership of. So solubility, I'm going to state the evidence. So sodium chloride solid is soluble. So we're not looking at mass, but it says explicitly rock particles are insoluble. In terms of particle size, why the rock particles are trapped? Well, if it says in terms of, you'd better be mentioning that in your answer. And the way filtering works is that you've got tiny pores in the paper, and if the particles are small enough to go through, they do, and if they're not, they're not. So they're too large. State the number of significant figures in the mass of the beaker with the dry NaCl. So there it is, our number right there. Our rule for significant figures is dot right, not left right. So there's a dot, we're going to be moving to the right across the number. We're going to find our first non-zero digit and then count the rest of them. So there will be 4 significant figures. All 4 of those digits there are considered significant. Show numerical setup for percent mass. Mass apart over mass a whole times 100. I copied that from table T for you. So we're just going to plug in because it doesn't ask us to calculate. We need percent mass in the rock sample. So I know the rock salt sample is going to be 16.4 grams. I don't really know what the NaCl is, but I'm going to write the times 100 there. Maybe I'll have to go back to my data and do some math. So the beaker with the dry NaCl is right there. The clean empty beaker, oh, well that'll be helpful. So we've got the dry NaCl and the beaker at 240, and we've got the clean and empty beaker at 224.2. So if we subtract the 2 of those, that should be just the difference shown by the salt. So we're going to go 34, 39.2, so it's 15.8 grams. And that's our setup. We can divide that out. I feel like we're going to get a high number. Around 90% of the mass was the salt, but we don't need to do that. They just say the numerical setup. So you won't be wrong for doing that, but I don't need to take the time to do it. So you barely need a calculator here, which is good. We've got 500 milliliters of gas, each of them at 101.3 kilopascals, 298 K. We've got H2 and N2. Okay, now we can take a look. Compare the mass of the gas in cylinder A to the mass of the gas in cylinder B. Oh boy. Avogadro's hypothesis says that if the temperatures and pressures are equal, then the number of particles and volume are proportional. Since these are the same volumes too, it's the same number of moles, number of particles, the same number. However, each particle has a different mass. Hydrogen is atomic number 1, so this is 2 per molecule. This is, that's wrong, it's the mass of 1. Nitrogens have a mass of 14, so that's 28 per particle. So the mass of cylinder B is going to be way greater than the mass of cylinder A. Don't get me wrong, there will be the same number of particles in both containers, but since the particles that are there are more massive, the mass of the whole gas is bigger for the nitrogen sample. A change in temperature and pressure that will cause the gas in A to behave more ideal. Well, it doesn't matter which one. The same change would make both behave more ideally. We want temperature to increase and pressure to decrease. This will cause your particles to spread out, to move faster, to take up less space of the total volume because the volume will go up. The attractions will be less present, less felt between the particles. This is all in all a very good change for ideality. In terms of collisions between the gas molecules and the walls of the container, again, we've got in terms of, so we're going to make sure we do that. Notice that we're saying compare and state and the answers that are coming out. A comparison means you got to mention both. The mass of B in cylinder B is greater than the mass in cylinder A. State a change, but it says temperature and pressure. So we're stating two changes, but we're just stating them, short answers. We're explaining, so now we need a sentence. In terms of collisions between gas molecules and the walls, why pushing on the piston at a constant temperature would increase the pressure? So if I don't change the temperature, the average kinetic energy won't change. The collisions won't become harder, but if we squeeze them down and make the gases take up less space, the particles don't get any smaller, the space between them gets smaller. You're going to get more frequent collisions with the particles and the container. The collisions with the container are really where the pressure is going to come from. You're going to get more force because there's more collisions and therefore a higher pressure. So force, don't forget, is pressure is equal to force over area. So if we increase the force, we'll increase the pressure. We also decreased the area by squeezing on the piston and making that area of the gas, smaller. But really here, I think, well, they work together. Numerical setup for calculating the volume. All right, I'm running a little bit out of space here, but we have our combined gas law. You know what? Let me shrink that really quick. We have, don't forget, all our data up top, and we need to change that into STP. So we want the volume in STP. This here is our initial volume. This is kilopascals is a pressure, and 298 K, that's a temperature. And then when they say STP, that's going to give us our T2 and our P2. So the first information is right in the question. The STP, if you forget, is found on table A of your reference table, which I've completely ran out of room to show here, but it is right there. There's a link above my head, don't forget. So let's just plug in. For temperature and for pressure on table A, there are two values listed. Here, we need our units to match, so the question is giving us the information we need. We have K, Kelvin, and kilopascals, kPa. We're going to copy those over. At standard pressure is 101.3 kPa, kilopascals, which is still the same. The pressures are the same. That's fine. We're showing the setup. We don't have to show that step. I'm going to, just to be really clear about what's going on. We don't know what the new volume is, and we're going to STP, which is 273 Kelvin. So that would be your setup. A rough guess, again, you don't have to solve it. I feel like you're going to get something in the 450 range, maybe. Don't quote me on that, but grab your calculator and check it if you want to get an answer for yourself, but you don't need to show that in your answer booklet. All right, we're almost done. Two more sets of questions. Conductivity of 3 solutions was measured. We have this solution, 0.1 molar, 6 molar, and 0.1 molar sugar. We're not going to really worry about the sugar. Looking at the questions, it says in terms of concentration of ions, why is this one more conductive than this? I know that conductivity is based on mobile charges, so if we have more conductivity, we have more mobile charges. And it says concentration of ions, so the concentration of ions in 6 molar HCl is greater. Now, you can't just leave it there. It says state why it's better than something else. So I think your answer should include that. I think including that it's greater than the concentration of ions makes the best answer. Identify the element. So we're just looking for a short answer. Makes it organic compound. It's this guy here. You're looking for carbons, and that's your identifier that you have an organic compound. All right, some nuclear chemistry. We've got 2 isotopes of phosphorus that we're going to look at, 30 and 32. They're telling us phosphorus 30 is positron emission, and then in your answer booklet, they gave you this formula to finish out, so I don't have to write the whole thing. But what I do need to know is that the total top numbers and the total bottom numbers have to be the same before and after the reaction, this transmutation that's occurring. So the total here has to be 15, that's a 1. That means this has to be a 14. The total has to be 30, that's a 0. That has to be a 30. And we look on our periodic tables for element number 14, and that should be Si. So through this positron decay, we're going to create silicon 30. Based on table N, determine the amount of time for a 100 milligram sample to decay, so there's only 25 left. The easiest way I've found to do these is to start with your given quantity, if you have one, and just keep dividing by 2. Each time you divide by 2, that's a half-life. And then you stop when you hit the target mass that they're asking about. And they said 25 milligrams, so we're done. And each time you've drawn an arrow, that's a half-life. So now there's been 2 half-lives, and it says that each individual half-life is 14.28 days. So we're going to take that information and say 14.28 days times 2, and that's going to be 28.56 days. And that's going to be our final answer. That's section B1. No, sorry, that's section B2. Thanks for watching.